Our 10th learning objective deals with reaction mechanisms. We are going to learn how to take reaction mechanisms and examine them, find what's called the rate determining step, and from that predict the rate law of a reaction. So this is another way to obtain a rate law that we have not seen at this point. So we start with reactants and turn into products, but it doesn't happen usually in just one fell swoop, one step of the one-step process. It takes a series of steps. These steps are called elementary steps. So they're simple reactions. What is colliding with what to produce a intermediate? And those things then react and run into each other and collide and produce something else on the way to a reaction. So the reaction mechanism is the sum of these elementary steps. It is that whole sequence of steps that come together that take you from reactants to products. Let's look at this reaction. We have 2NO and O2 producing 2NO2. This is an observable fact. When you're monitoring that reaction, you find that some N2O2 exists, but just for a brief time. It is not a reactant, it's not a product. So what would that mean? Well, that can't possibly mean that two molecules of NO collide with one molecule of O2 and out pops some NO2. It means that on the molecular level that the two molecules are doing something else. Okay, so they do not collide to produce it in a one-step process. Here is what is proposed, and this would account for the observance of the N2O2. And NO collides with an NO. That produces N2O2. Then the N2O2 can collide with an O2 to make the final product. These are the elementary steps. Okay, those are your elementary steps of this mechanism. They have to add up to give you the overall reaction. So these N2O2s will be able to cancel out when you add these reactions together. They are intermediates, so they appear in the mechanism for a brief time, but they are not in the overall reaction. They get produced in an early elementary step and then consumed in a later step. So we see here it's getting produced in this step and it's getting consumed in this step. So we see they would cancel out as you add those together and give you the overall reaction. Now your elementary steps must add up to give you an overall reaction that you're looking for, otherwise it's certainly not a good mechanism. You use experimental evidence to help you support the steps that you choose for a mechanism. Now you're not going to be given a reaction and asked to determine the mechanism, but you ought to be able to look at a mechanism and see if it's a realistic or plausible mechanism for a reaction. Some terminology that goes along with this concept. A reaction is, an elementary step is unimolecular if it only has one reactant. It's bimolecular if it has two reactants, two molecules. So it's basically showing the collision. What has to collide? Two molecules have to collide in order to produce a bimolecular. That is by far and away the most common elementary step. A termolecular, which is very rare, would be three molecules colliding into single space in order for a reaction to take place. It is rare because it's difficult for three molecules to actually collide if they're all moving about randomly into a single space and time. Okay, so here is a question for you to consider and to answer. We have that mechanism. What are the elementary steps in this mechanism? Well, if you chose bimolecular, then you are correct. Now, when you look at elementary steps and you want to come up with the rate laws of those elementary steps, you actually can, and I will put a star by that, you actually can use the coefficients to determine the orders of those elementary steps. Now, this you couldn't do for an overall reaction, but you can for an elementary step. So if this were an elementary step and we see a 1 coefficient for the reactant A, we can raise it to the first power here. And you know that we don't write the first power down. A plus B going to products. We have the reactants A and B, both raised to the first power. If an elementary step looks like this, an A has to collide with an A to produce products, then that would be the same as 2A, but we usually don't write it that way simply because we are showing the collision of what collides with what when we write our elementary step, but that would give us a second power for A. Now remember this, and this is so important to note, okay, because students after they do this want to go back to an overall reaction and use the coefficients. This does not apply for an overall reaction. How do you determine for an overall reaction? Experimentally. You have to determine it experimentally. But once you determine it experimentally, we're going to see that our rate law needs to support that experimental information. One of the steps in our mechanism is going to be called a rate determining step, and it's the slowest step. It is what is going to determine how fast the overall reaction is. It can only be as fast as the slowest step. This elementary step that we determine to be the rate determining step is whatever rate it goes at, whatever speed that slowest step proceeds at, is the speed or the rate of the overall reaction. Now, to give you a good feel for this, we're going to look at a specific example. So you're going to see me constructing these little booklets, and from that process be able to determine the rate determining step and see how that actually determines the overall rate of the reaction.
We're going to simulate a mechanism and talk about a rate determining step through the simulation of this mechanism. It's going to have 3 steps. Our final product is going to be a little booklet. So we're going to staple this booklet together. The booklet's made of an orange sheet and a blue sheet. There's going to be 3 steps to this mechanism. One person is going to collate the sheets together. One person, that's going to be me, is going to fold them into 3 parts and hand it off to the next person who's going to staple the booklet to give us this final product. So what we just demonstrated was a process that represents a chemical reaction taking place. And it's representing a three-step mechanism. We have the collating of the pages, we have the folding of the pages, and we have the stapling of the pages. And if we're going to look at the overall rate of the reaction, we don't look at from beginning to the end and say, how long did that take? We look at it coming off the assembly line and say, how many can we produce in a certain amount of time, and monitor that. So that's what you first need to realize about rates. It's not start to finish, but coming off the assembly line. So we produce 6 booklets in 45 seconds. So if we were to find the rate, we'd do 6 divided by 45, and that would be booklets per second. And now we want to think about what is the rate determining step of that process. We have the process of collating, putting the 2 pieces of paper together. And if we sped up that process, it wouldn't come off the assembly line any faster. And we had the stapling end of the process, which, you know, if he could staple just really, really lightning fast and staple as fast as he could, still wouldn't come off the assembly line any faster. But my step, which is to meticulously fold it in a trifold, put them together and toggle them and fold it, that was a slow step. Now, if I could figure out a way to do my step faster, that would speed up the overall process. So we'd call this the rate determining step.
Okay, now that you have an understanding of the rate determining step and how it drives the reaction, let's examine another mechanism. So we see the overall reaction above, and we see that somebody went and experimentally determined this to be the rate law for the overall reaction. Now here is the proposed mechanism. It's a 3-step mechanism, and we've got some things to observe. First thing we want to figure out is which step would be the rate determining step. Well, the way that you would figure this out is to come up here and write the rate laws for each of these elementary steps. For this elementary step, rate is equal to, and we're going to call the rate constant K1 because this is just step 1, times H2O2 raised to the first power, and I minus raised to the first power. For this reaction, rate is equal to K, and I'm going to give it a K2, it's a different rate constant, times OH minus times H plus, both raised to the first power. And this one is rate is equal to, and I'll give it K3, HOI times H plus times I minus. Now we have to look and say, okay, which one of these rate laws match the overall rate law? Well, that would be this first one here. It matches that. And that will tell me that the first step is the rate determining step. Now, if none of those match that overall rate law, something else is going on that we haven't discussed. Or you've got a bad mechanism. Now we see underneath here, I've written some words, that this one would be the slow step because it was the rate determining step. And its rate is exactly equal to the rate of the reaction. That's the slowest step, is as fast as this reaction can proceed. Now what you need to understand is it's not the sum of these rates. We don't add them up to determine the rate of the reaction. It's how fast it's coming off the assembly line, and it's going to come off the assembly line as fast as we can do this reaction here. Okay, we see down at the bottom of this page the mechanism that was on the previous page that we determined the slow step for. I want you to look at that mechanism and determine which substances are the intermediates. Now remember, intermediates are a substance that disappear in the overall reaction. They would get canceled out, but they get produced in an early step and reconsumed in a later step. Okay, if you chose number 4, then you are absolutely correct. Those are your intermediates. So we have this substance being produced and then consumed, so it's not in the overall reaction. We have OH minus getting produced and consumed. Everything else is part of the overall reaction. Okay, so this is the end of our Learning Objective 10, where we were determining a mechanism, looking at mechanisms and seeing how we can predict rate laws from those mechanisms, and learning about the slow step and the rate determining step.